At the end of this lesson, you will be able to factor a polynomial using the greatest common factor to show how you can rewrite the polynomial as the product of two different expressions. First, we must know what factors are. Factors are expressions that multiply to give you a product. So, for example, we can list the factors of the number 30. I like to start with the smallest factor, 1, and the largest factor, 30, the number itself, and then I like to list them as pairs as I go through the list. So 1 can divide evenly into 30, 30 times. 2 can divide evenly into 30, 15 times. If I can multiply 2 times 15, the product of these two expressions gives me 30. 3 divides evenly into 30, 10 times. 4 does not divide evenly into 30. The 5 does. It divides evenly 6 times. And then now I've already seen 6. 7 does not, 8 does not, 9 does not, 10 does. I already have it listed. And that means that this list is complete. I have all of the smaller factors, and then they loop around to the larger factors. So now we can list all of the factors for the number 24 the same way. I have 1 and 24 itself, 2 and 12, 3 times 8, 4 times 6, 5 is not a factor of 24, 6 is, it's already listed, this is my complete list. You have a choice. You can list them as pairs, or you could just list them out like this, 1, 2, 3, and then not 4, but 5 will go into 30, 6, 10, 15, and 30. The reason I prefer the pairs is I find that I will miss less factors. When I list them out like this, sometimes I'm afraid that I might skip a factor. Okay, so factors are expressions that multiply to give you a product. If you can find the factors of numbers, we can also find the factors of variables. So let's take a look. If I have x squared, its factors are 1 times itself, times x squared. I could also have x times x. Here I have a cubed times b squared. Its factors could be 1 times a cubed b squared. I could also have a cubed times b squared, or I can fully expand it as a times a times a times b times b, or even a squared times another a to make a cube times b squared, or I could break it apart to b, and so on. There's a much longer list when variables are involved. Let's take a look at the last example. I have x to the 4th y cubed, so 1 times itself. I could also rewrite this as the product of x to the 4th times y cubed. Could also be x squared times x squared to get x to the 4th times y squared times y to get y cubed. We could also fully expand with x times itself 4 times, y times itself 3 times, and so on. Okay. Now the greatest common factor, the GCF. This is important for today's lesson. It is the largest monomial, which could be a number or a variable or a mixture of the two, that divides into all the terms, into all the terms of a polynomial. So let's start off with just numerical examples. If I wanted the GCF of 18 and 24, I should list out my factors of each number. So the factors of 18 are 1 and 18, 2 and 9, 3 and 6, 3 times 6, 4 is not a factor, 5 is not, but I've already have 6 listed, so this is a complete list. Let's list the factors of 24 again. I have 1 and 24, 2 and 12, 3 and 4, and nope, 3 and 8, rather. 3 times 8, 4 times 6, that's our complete list. The greatest common factor is the largest factor that they have in common. So the largest number that they both have in common as a factor is 6. So the GCF would be 6. Okay, let's look at the next one. If I have 5y and y, well, 5y has a few factors. I could have 1 times 5y. I could have 5 times y. For y, I just have 1 times y. So their greatest common factor, what's in common here, is just y. So the GCF here is the variable y, or 1y. For the next example, we have 16x and 32x squared. So 16x, let's break this apart. I have 1 times 16x. I could also break apart the coefficients separately from the variable. The coefficient can be listed as 1 times 16 times x. I can have 2 times 8 times x. I cannot have 3, but 4 times 4 times x. Since 4 is a repeat factor, that is my complete list. 5 won't work, 6 won't work, 7 won't work, and I'm back at 8 and then up to 16. So now if I list the factors of 32x squared, I have 1 times 32x squared. Now this one can be broken up many ways as well. I can have 1 times 32 times x squared, or 1 times 32 times x times x. I could also list this out as 2 times 16 times x squared, or 2 times 16 times x. Now, you can see that this can get very tedious or pretty annoying trying to list them all out all different ways. So instead, you can use your knowledge of common factors for the coefficient separately from variables. 4 times 8 times x squared, or 4 times 8 times x times x. 5 is not a factor, 6 is not a factor, and neither is 7. But here we can see that not only is 8, or 16 rather, 16 is a common factor, but they also have a common factor involving the x. This one would just be 16 times x. This is 32 times x times x. The most amount of x's that they have in common that I could take from both is 1. 16x doesn't have an x squared to take. So my GCF here is the greatest amount that they have in common, so the GCF is 16x. You can of course get here without having to list out every single way of multiplying to get 32x squared as a product. Okay, for this example, let's try it a little bit in a quicker way. I have 18 times A times B times B. And then I have 3 times A times A times B times B times B times B times B. Okay, first let's start with numbers. The GCF here between 18 and 3 said I can divide them both by 3. So we can use that as our numerical GCF. But now let's look at these A's. I have one A that I could take from both that they have in common. And then the most amount of B's that they have in common is 2 of them, so it would be 3A B squared. Okay, the reason we've been reviewing greatest common factor is because of this factoring method that we're about to use. It's similar to backwards distribution, meaning we're going to predict what was on the outside and what was here on the inside of a set of parentheses before arriving at a certain product or answer. So to predict, we use backwards distribution to factor out the GCF. Our goal is to rewrite the expression as the product of 2 expressions. So we want to take something that was one single polynomial and rewrite it as the product or the multiplying of 2 different expressions. So let's check it out. For these examples, we can rewrite each of them so that they are equivalent to the product of more than one expression. So let's start with the first one. This is the same as, well, the number that's in common between 15 and 10 that I could divide them both by. I'm trying to think, is there something that could go out here that was distributed into the parentheses and ended up with 15 and 10? And that common factor is 5. So now 5 would have multiplied with 3 to turn into 15, and 5 would have multiplied with 2 to turn into 10. But now let's talk about these variables. They are different. So there is not a variable out in front as part of my GCF. Instead, 5 times 3c is what gave me 15c, and 5 times negative 2d is what caused this to be negative 10d. So our final answer is right here, 5 times the binomial 3c minus 2d. This is now the product of two separate expressions. Let's take a look at the next one. If I had 6 and 18 in a list, the greatest common factor numerically would end up being 6. I could divide 18 by 6 and 6 itself by 6. So now we're trying to predict if there are any other variables in common, and there are not. So now inside the parentheses, 6 must have been multiplied with y squared to get 6y squared, plus, and 6 times 3 would end up with 18 as the answer. So this expression, 6y squared plus 18, is equivalent to the product of 6 and y squared plus 3. Example 3. Now I see two variables, a single variable, and then numerical coefficients. Let's see what they have in common. Well, between 10 and 5, we all know that a common factor would be 5. They're both divisible by 5. So let's start there. So this 10 and this 5, I could divide by 5. Now I also see that there is an a in common in both, and the highest power in each is just to the first power. So now, instead of just having 5 on the outside, let's predict what this binomial was that 5a multiplied with. 5a times 2 would give me the 10, but it also needs to have a b appear, so it must have been 2b. Plus, now 5a times something stayed 5a. The only number you can multiply with and remain the same is 1. Okay. And the next example starts out with a binomial that has two terms, each of which have two variables. So let's take a look at what we can do here. This is going to equal, let's see, the greatest common factor among 12 and 18. Well, let's see, 1 and 12, 2 and 6, 3 and 4, and then we have 1 and 18, 2 and 9, 3 and 6, 4 doesn't work, 5 doesn't work, so our greatest common factor here must be 6. 6 is the largest number I could divide from both coefficients. Now let's look at the expansion of the variables. This is the same as x times y times y times y. Here we have x times y times y. Let's see. So we have an x and an x in common. X can be part of my GCF. We also have y squared in common. There's two y's that I could take from both. And now let's say what must be inside parentheses. So 6 multiplied with 2 to turn into 12. Now x is still here. This is now supposed to be a y cubed, but this only has y squared, so it must be multiplied with y to the first y. So at least 1 power of y, which can be written as an exponent, or it does not have to be. Alright, so now we have plus 6 times 3 would turn that into 18. We already have the only x, and we already have the y squared that we need. So our final answer here is 6x y squared must multiply with 2y plus 3. Now, how can we check our answers? Well, pretend that we started with the answer and we were working the other way. We have to distribute. Instead of backwards distribute, we want to distribute or multiply to check. So let's just check our last answer. If I distribute this, I end up with 6 times 2 is 12. X stays x. Y squared times another power of y gives me y cubed. So far, so good. Plus 6 times 3 gives me 18. And there's no other variables here, so I still have xy squared, matching my original problem. So this is the correct answer here. This concludes our lesson. We are now able to factor a polynomial using the greatest common factor so that we can rewrite the polynomial as the product of two other expressions. We will practice again tomorrow in class. Thank you for watching.